The next couple of algorithms we'll look at can be written recursively, and they're often written recursively. So let's take a brief time out and talk about recursion to make sure we're all on the same page. A method is a recursive method when it calls itself. So we're going to take a look at calculating the factorial for a number. As a reminder, to calculate the factorial, you start with the number and then you multiply it by number minus 1, and then you multiply the result by number minus 2, and you multiply that result by number minus 3, etc. until you hit 0, and then you stop. So 3 factorial would be 3 times 2 times 1, which equals 6. 100 factorial would be 100 times 99 times 98 times 97, all the way down to times 1. And that the result of that is 9.332622 to the power of 157, which is a pretty large number. Now, how about 0 factorial? Well, by definition, that's equal to 1. So 0 factorial is 1. Now, if you're wondering about negative numbers, the factorials for negative numbers are undefined. Okay, so I have on the screen the factorial algorithm, the steps for calculating the factorial. We start out by saying if num is equal to 0, so if we're taking num factorial, if num is equal to 0, then the factorial is 1, and we stop. We have the result. Otherwise, we set the multiplier to 1, and we set the factorial to 1. And then while the multiplier is not equal to num, we do steps 5 and 6. We multiply factorial by multiplier, and we assign the result to factorial, and then we add 1 to multiplier. And so we'll say 1 times 1, add 1 to multiplier, so multiplier will become 2, so we'll have 1 times 2, and then we'll assign 2 to factorial, and then we'll multiply that by 3, and so we'll assign 6 to factorial, we'll multiply that by 4, assign 24 to factorial, etc. And we keep going until multiplier is equal to num, at which point we stop. So that's another way of looking at it. Instead of counting down and going 3 times 2 times 1 for 6 factorial, we can also say 1 times 2 times 3. It'll give us the same result. So in this algorithm, we basically have a rinse and repeat step, which is step number 4. Step number 4 says that while the multiplier is not equal to num, do steps 5 to 6. So how would we code this? Well, let's go out to IntelliJ and we'll write the function that calculates the factorial in an iterative way. So we'll use a for loop. So here I am in IntelliJ, and I've created a project. The package is academy.learnprogramming.recursion, and I'm going to write a method to calculate the factorial in an iterative fashion, and that means we're not going to use recursion. So I'm going to say public static because we'll be calling it from the main method. It's going to return an integer, the factorial, and I'll call it iterative factorial. And of course, we want to pass in num. So the first thing we'll check is whether num equals 0, because if num equals 0, we know that the result is 1. And so we'll just return 1. If num doesn't equal 0, we'll set a field called factorial to 1, and then we'll say for int I equals 1, I less than or equal to num, I plus plus, factorial is assigned factorial times I. And when we drop out of the loop, we have the factorial, so we'll just return that. So what's happening here? Let's say we wanted to calculate 3 factorial because we know that that's 6. So num is not equal to 0, so we don't return. We'll set factorial to 1. I has to be less than or equal to 3, so we're passing in 3. So on the first iteration of the loop, factorial will be assigned factorial times 1, and we start out with factorial being 1, so factorial will get 1 times 1, which is 1. I will become 2, so factorial gets 1 times 2, which is 2, and then I becomes 3, so factorial gets 2 times 3, which is 6, and then at this point I becomes 4. It's no longer less than or equal to num, so we drop out, and so we return 6. So that means 3 factorial is 6. And so this is an iterative implementation. We're not using recursion. The method does not call itself. So what about a recursive implementation? Well, instead of using the loop, we can have the method call itself, because think about it. 2 factorial is 1 factorial times 2. 3 factorial is 2 factorial times 3. 4 factorial is 3 factorial times 4. I'm going to write these out in a comment so you can see what I mean. So 1 factorial, and usually we write factorial using exclamation marks. So 1 factorial equals 0 factorial, which we know is 1 times 1, which equals 1, right? 2 factorial equals 2 times 1, and this is actually 2 times 1 factorial, because we know that 1 factorial is 1. 3 factorial equals 3 times 2 times 1, and that's equivalent to 3 times 2 factorial, right? Because 2 factorial is 2 times 1. So that's 3 times 2 factorial. 4 factorial is equal to 4 times 3 times 2 times 1. And that's equivalent to 4 times 3 factorial, because 3 factorial is equal to 3 times 2 times 1. So you can see the pattern now. So 1 factorial is, I guess I should reverse that for consistency. So 1 times 0 factorial. 2 factorial is 2 times 1, which is 2 times 1 factorial. 3 factorial is 3 times 2 times 1, which is equivalent to 3 times 2 factorial. 4 factorial is 4 times 3 times 2 times 1, which is equivalent to 4 times 3 factorial. 5 factorial would be 5 times 4 times 3 times 2 times 1, which is equivalent to 5 times 4 factorial. And so to calculate each factorial, we can use a factorial. Basically, we multiply the number, by n minus 1 factorial. So basically, we're doing the following. To get n factorial, that equals n minus 1 factorial times n, right? I'll do it like that because that's how I wrote it above. So basically, this is the formula we can use to get the factorial of n. It's equal to n times n minus 1 factorial. And so let's write a method that uses this information. So we'll say public static int, and we'll call this one recursive factorial. And we'll pass in num as we did before. And we'll start out the same way. If num equals 0, then we return 1. We know that 0 factorial is 1. Otherwise, what are we going to return? Num times recursive factorial of num minus 1. Because we've just said that we can calculate the factorial of n by multiplying n by n minus 1 factorial. And so here we're calling the same method. We're calling the method itself to get the value. And here you can notice in the getter, IntelliJ has added this icon here to tell us that we're making a recursive call. But how does this actually work? Let me move this up. So let's say we call recursive factorial with a value of 3. Well, we're going to say, does num equal 0? No, it doesn't. So we'll come down and we'll say, okay, we want to return 3 times recursive factorial of 2. Now this doesn't return right away because what's going to happen is we have to wait until we get the value of recursive factorial num minus 1. And so what will happen is the call to recursive factorial with a value of 3 is going to be pushed onto what's called the call stack. And then recursive factorial 2 is going to be executed. So we haven't returned from recursive factorial 3 because we have to wait for this result. And then we come into recursive factorial with 2 into this call. Num isn't 0, so this time we're going to want to return 2 times recursive factorial of 2 minus 1, which is 1. So now the recursive factorial call with the value 2 has to wait. And so it's going to get pushed onto the call stack, and recursive factorial 1 is going to be called. So basically at this point we have 2 calls to recursive factorial that are waiting for a return value. We call recursive factorial 1. Well, 1 isn't 0, so we're going to come down here and return 1 times recursive factorial of 1 minus 1, which is 0. So now the recursive factorial call with 1 is going to get pushed on the stack because it's waiting. And we call recursive factorial 0. So we're going to come in here. This time num is 0. So we return 1, and this call is finished. It doesn't get pushed onto the stack. But now the recursive factorial call with 0 returns, and that's the call that recursive factorial with the value 1 is waiting for. So now that call can resume, and it gets a return value of 1. And so it multiplies 1 by 1, and it returns 1. And now the call to recursive factorial 2 can resume because it was waiting for the return value of recursive factorial 1. And so it multiplies 2 by 1 to get 2. It returns 2. And now the call to recursive factorial 3 can resume because it was waiting for the return value of recursive factorial 2. And so it multiplies 3 by 2. It gets 6. It returns, and we have finished. There's no more calls to recursive factorial waiting on the call stack. And so 6 gets returned. But you'll notice that the order in which the recursive calls are made, they return in the reverse order. So basically the situation that we have, so we start out with calling recursive factorial 3, and when it hits this line, it calls recursive factorial 2. So it can't return until it gets the value of recursive factorial 2. And so the call to recursive factorial 3 gets pushed onto the call stack. Then recursive factorial 2 is called. It can't return until it gets the result of recursive factorial 1. And so it gets pushed onto the call stack. And then recursive factorial 1 will get pushed onto the call stack, and recursive factorial 0 will actually return right away. So when recursive factorial 0 returns, this gets popped off the call stack, and it continues executing, and it will return 1. And when that returns, this gets popped up off the call stack. It continues executing and returns the value 2. And finally, this gets popped off the call stack, and it returns the value 6. That's how recursion works. And it's important to see that when you enter a recursive method, it might be a while before it returns. You can go down the rabbit hole and you can go deep. So when you see recursion in the upcoming sort algorithms that we're going to look at, keep in mind that the call to a recursive method may result in many more calls before it returns. So it's important to understand that a 3-line recursive method could result in hundreds of recursive calls. The code might look simple, but it can lead to a ton of processing. And it's really important to understand that none of the recursive calls return until they receive the result from the method that they invoked recursively. So as we saw, recursive factorial 3 invoked recursive factorial 2. So recursive factorial 3 is not going to return. It can't return until recursive factorial 2 has finished executing. Now you'll notice here that the recursive calls are ended when we pass num equals 0, because when we pass in num equals 0, we don't make a recursive call. We just return 1. If we didn't have this condition, we'd never end. We just keep making recursive call after recursive call after recursive call. So in order for recursion to work properly, you need some condition that's going to end the recursion. And that condition is known as the breaking condition, and it's also called the base case. So in the recursive factorial method, this if num equals 0 condition is the base case, or the breaking condition. At that point, when num equals 0, we say that the recursion starts to unwind. So at that point, it's going to return a value, and the method that invoked it recursively will now be able to continue executing, and then it will return a value, and the method that invoked it recursively will be able to continue executing, etc. So when you use recursion, you need a breaking condition. If you don't have one, what will happen is the method will keep calling itself recursively, and eventually you'll get a stack overflow exception, because the call stack only has a certain amount of memory allocated to it. And so eventually you'll blow that memory. So let's run our recursive code. Well, we'll run them both actually. So Let's system.out.println, and we'll print out iterative factorial of 3. And we'll do the same thing for recursive factorial 3. We should see 6 in both cases. Let's run. And sure enough, we get 2 6s. For fun and giggles, let's remove or just comment out this breaking condition. And you're going to see what happens here. It's not going to be pretty. And look at that. We get all these recursive calls until eventually we get a stack overflow error. And so this method just keeps calling itself and calling itself and calling itself, and there's nothing to stop it from doing that. And so we have all these, you're actually looking here at the call stack here. So you're looking at all of the methods that are on the call stack. And as you can see, it just keeps invoking itself until we blow the call stack space. I'll uncomment that now. Okay, so that's recursion. Now here's something interesting. The iterative implementation usually runs faster and it doesn't use as much memory, because there's overhead involved with pushing method calls onto the call stack. And each stack frame uses some memory. But sometimes the iterative way isn't as intuitive, or if you write the algorithm in an iterative way, it'll be like a 500-line method or something like that. So developers still use recursion because it's often the most elegant and more easier to understand solution. Now, when we're dealing with a recursive method, the call stack can also be referred to as the recursion stack. And we saw that when we don't have a breaking condition, we'll get a stack overflow exception. It's possible to get that exception even when you do have a breaking condition. If you write a recursive method and it invokes itself 1,000 times, you're still possibly going to get a stack overflow exception because you're not hitting that breaking condition. So even if you have a breaking condition, if you call the recursive method with something that's going to cause the method to invoke itself 1,000,000 times, you're going to get a stack overflow error. So just keep that in mind. Now, there is a way around this potential blowing of the stack. It's called tail recursion, but we're not going to see that for 2 reasons. First of all, none of the algorithms we look at, none of the implementations use tail recursion. But the second and perhaps more important reason for Java is that the Java compiler doesn't use tail recursion. So we can't use that type of recursion in Java. I'm just mentioning it to make you aware that it exists. And if you want to read up on it yourself, I've linked to a Dr. Dobbs article in the resources section. So if you're interested in reading about tail recursion in Java, you can go ahead and take a look at that article. Anyway, I hope that this has refreshed your memory about recursion. And now that we're all on the same page, we're going to move on and look at a recursive sort algorithm called merge sort. I'll see you in the next video.